Alright, hey guys, and welcome back to another AP Physics C video. Today we're going to be continuing the major derivation series with the derivation of current as a function of time for an RC circuit while it's charging. So let's look at the circuit first before we even do anything. This circuit has a voltage source slash EMF slash battery epsilon, right? We see that here on the left. It has a capacitor with capacitance C. We see that here on the right. And it has a resistor with resistance R, which we see on the top, right? So now looking at the circuit, you might say that it's incomplete and there's no current flowing through it, right? And you'd be absolutely right. So in order to get through this derivation, we're actually going to close this switch, right, to position 1, right? And now closing it to position 1 makes it so that this circuit element, this part of the circuit, has no current flowing through it because it can't be in a loop with anything else, right? You need a closed loop to have current flow. So we'll just take that out. And now this is what our circuit looks like, right? So let's just jump right into it. When we analyze a circuit and we seek to derive anything as a function of time, we will usually immediately look for a closed loop in which we can apply Kirchhoff's loop rule. That's why I took out that other circuit element, because there was no closed loop. It was not contributing to the circuit, right? There would be no current through there. This actual circuit, right, this outer part of the circuit is really what we need to look at. And if I haven't mentioned it already, we want charge as a function of time in this video, right? You might have been able to tell by the title, but yeah, now we're gonna continue, right? So I said Kirchhoff's loop rule, right? So if you're not familiar, Kirchhoff's loop rule states that the sum of all voltage drops and rises around any closed loop in a circuit is equal to 0. Now, normally you might be thinking about labeling each corner and junction with a letter, right? So like this corner, this corner, this corner, this corner, right, with letters, and declare some loop A, B, C, D, A in which you can apply Kirchhoff's loop rule, right? But this often can be like a waste of time on the exam. So we're not going to do that, and we're rather just going to apply Kirchhoff's loop rule without these labels, because on the AP exam, you will not have labels. I can't actually say that for certain, but in the past exams that I've seen, they don't give you labels on each corner, right? Unless it's a multiple choice, but they could, right? They've been more lenient these years, but they usually just give you a circuit. So now we're going to look at this circuit by writing the loop rule here, right? So let's start before the battery at this bottom left corner. So this bottom left corner, we're going to look and start the loop from here, right? So if we go up, we're going to go to the battery and through it and our path, right? We can see that this will give us a positive potential difference. So we're going to start Kirchhoff's loop rule by writing the voltage rise from the battery, which would be epsilon, right? Without a negative sign, just like this. Then as we go around the circuit, as we trace that loop around the circuit, we follow that path. Our next circuit element will be the resistor, which gives us a negative potential difference because resistors resist the flow in currents by applying a negative potential difference to moving charges. So let's just write the potential difference, right? So negative IR, because by Ohm's law, V equals IR, right? That's one of the first things you learn in Physics C. And then as we follow this around the circuit, right, this path, this Kirchhoff loop, our last circuit element will be the capacitor, which applies another negative potential differences to the charges that move through it. And it does this in order to get them to stop moving and stay on the plates, right? That's just what a capacitor does. It builds up charge by applying that negative potential difference, and that negative potential difference is Q over C, right? Because of that one law, Q equals C delta V, right? If we rearrange that for the delta V, we get Q divided by C. Enough said about that. And now we'll follow this loop around the circuit back to the starting point. And now we have that whole complete loop, this whole complete loop around the circuit. So we have summed up all of the voltage drops and rises. So we can say that all of those drops and rises, the sum of them is equal to 0. Now we have just written a Kirchhoff's loop rule for this circuit. But to make this equation a little easier to work with, we're going to multiply C, the capacitance, to the whole thing, right? To both sides, giving us this next equation. So we're going to multiply by C like this, right? Oops. Like this. And we're going to get EC minus I RC minus, and then C times Q over C is just Q. And then 0 times anything is 0. We're going to get this equation, right? Now, here is where the magic happens. Notice that we have I. current in this equation, right? So on your AP Physics C equation sheet, you'll notice that I is equal to dq dt. So we're going to sub that into this equation and get a new equation. So EC minus, like I said, dq dt times RC minus Q is equal to 0, right? We get this full equation. Now this equation is known as a differential equation. This differential equation helps us recover the original function q of t, whose rate of change is described by the derivative dq dt, right? The dq dt being the current. This is what we need. We need that dq dt in order to derive q of t. You'll always do this whenever you're doing some sort of circuit derivation, some sort of function as a time derivation. You'll always start or always do it through a differential equation. But before we even think about solving this differential equation, I'm going to introduce two constants that will make this process a little bit easier. So the first constant is called the time constant, and I'm going to do that down here in a different color. We're going to do red. We're going to call the time constant is tau, right? This is the same symbol that we use for torque in mechanics, as you may notice, but that's not really relevant. They're not related, right? The time constant is equal to the equivalent resistance of a circuit times the equivalent capacitance of a circuit, right? Of an RC circuit, correction. In this instance, that would simply be, right, R times C, because we have no other, right, resistors or capacitors to make this equivalent. But if we did, right, like this, that's bad. If we did kind of like this, you could imagine you would just find the equivalent capacitance and then adjust the time constant accordingly, and then you would be able to derive the same thing. It's the same process, right? And this constant will tell us how fast the circuit charges. A larger time constant with this specific scenario, in this specific instance for charging, means a slower rate of charging. So I'll say that again. The time constant tells us how fast the circuit charges. A larger time constant means a slower rate of charging, and vice versa. A lower time constant means a higher rate of charging, right? So now let's sub that time constant tau into the equation. So we're going to do that here, dq dt, and right here you see RC, R times C, time constant is tau, right? Simple enough. And now the second constant, right, we're going to call it Q infinity, right? We're going to write that in pink over here, or no, that's hard to see, in blue, right? So Q infinity looks kind of like this, right? It represents the maximum charge that will eventually accumulate on the capacitor, right? So in this circuit, right, Q infinity is going to equal epsilon times C. Why, you may be asking? Well, when this capacitor is fully charged, no more current is going to flow through the circuit. That's a key fact of RC circuits. Once it's fully charged, the capacitor resists any more incoming charge, right? So the current will have to drop to 0. At that moment, by Kirchhoff's loop rule, right, we'll do another one in this cyan color, imagining this to be gone because there's no more current, right? The resistor serves no purpose. The voltage across the capacitor must be equal to the voltage of the battery, since there is no longer any voltage drop across the resistors. So it's as if we took this original equation and just took this part out. And the equation with that taken out would be epsilon minus Q over C is equal to 0. Mind you, when I said that, I was referencing the voltage drop across the resistor, right? And this is the new Kirchhoff's loop rule for when max charge is reached on the capacitor. And if I do some rearranging with algebra, I get epsilon is equal to Q over C. And if I multiply C by both sides, you'll notice I get epsilon C is equal to Q infinity. And the reason why I wrote Q infinity and not just a regular plain old Q is because in taking that voltage drop, IR, from the resistor out of the circuit, right, out of the Kirchhoff's loop rule, I'm identifying the loop rule for when max charge is reached, right? Because only when max charge is reached can you take that voltage drop from the resistor out, right? So hopefully that makes sense, and now you can see why Q infinity is equal to epsilon times C, right? So now I'm just gonna make sure none of this blue stuff is left over, because I just wanted to explain why Q infinity is epsilon times C. But now that that's been explained, we can go on and sub in q infinity into this equation. So let's just do that here. We have EC, right, on this left-hand side. So we're just gonna, sorry, not EC, epsilon C. We're just gonna sub in that q infinity and rewrite the rest of the equation as it was, giving us this beautiful equation, right? Now we have this differential equation with our constant subbed in. It's much easier to work with. And now and only now are we going to solve this differential equation in order to get q of t, right? Charge as a function of time. And we're going to do this using separation of variables, right? This is usually the case in AP Physics C because they can't really test you on other means of solving differential equations. There's a whole class actually dedicated to that. But usually in AP Physics C, it's only separation of variables. Right here, I'm going to do that. I'm going to just get my q's on one side and my t's on another and integrate both sides in order to get q of t. So let's just do that like so. Let's move our q. I'm just going to move that this way. And then I'm going to add dq dt to both sides. Oh, I forgot it's being multiplied by tau, right? We're going to add dq dt times tau to both sides. And now I'm going to get q infinity minus q is equal to dq dq dt times tau. And now there's something I really want to note here. There's two ways to go about continuing this differential equation. One would be to multiply -1 to both sides, giving us this equation, q minus q infinity is equal to negative tau dq dt, or to just leave the equation as is, right? And then separate the dq and the dt to their respective sides, right? Now you might be asking, well, why would you ever multiply -1? Doesn't that seem kind of pointless? Well, in this instance, and actually whenever you're trying to derive something as a function of time for circuits, it actually isn't pointless, right? When in your final equation, it'll show up in a specific form that I'll talk about in the end, where you'll see that the term tau is always multiplied by a negative, whether it's t over tau, 1 over tau, usually it'll be t over tau. You'll always need that negative times tau. And this will just also make the integration process easier. So I'll just show you that, right? Let's just do the integration process for both of these sides. I'm going to start with the left, right? So when I separate my variables, I need the dq's. I need this q to line up with this q. So I'm going to actually divide by q minus q infinity. That's a really bad q infinity. Q infinity. And then divide by the same thing over here. And now I get 1 is equal to negative t dq over dt, 1 over q minus q infinity. And remind you, this negative tau is still being multiplied. So I want the dt by itself, so I'm actually going to multiply dt over negative tau to both sides. And this would be a hassle, but I'm just going to copy paste. Copy paste to both sides. This looks a little bit large, but I'll just walk you through it. This negative tau will cancel with this dt will cancel with this, and I'll get that this new equation turns into dt divided by negative tau is equal to 1 over q, 1 over q minus q infinity dq. Right, so now 1 over q minus q infinity times dq is equal to dt over negative tau. Now I could have kept negative tau on this side, but I personally don't prefer doing it that way because tau is a time-related thing, and I like to keep it on the time side, right, with the variable time. And now the way you would solve this, right, you would integrate both sides. But now this is the issue. Normally when you're solving a differential equation for calculus, you won't apply limits, right? You usually won't need limits. But whenever you're doing AP Physics C, whenever you're solving a differential equation for AP Physics C, you need limits. It's very common to have limits. It's honestly uncommon to not have limits. So the limits for this situation will just look at the circuit, we're going to think, okay, well, what do I want the function of time to vary from? Well, I want time to start at 0, right? And I want it to end at some arbitrary value t, right? Where t is time, right? And the charge, I know that the charge is going to start at 0, right? Because when the circuit is, when this switch is unclosed, right? The charge has to be 0. And when I start my time, when I close the circuit, right, the charge will begin to accumulate on the capacitor. And at some random time, at some time t, the charge will be q of t. So these are our limits of integration that we're going to use. And now we can just solve these like regular integrals, right? On the left-hand side, I'll take out my constants from the left. Integral 0 to t dt is, and on the right-hand side, I'll just actually rewrite it because I want to focus on the left-hand side. And this is 0 to q of t, dq. And we know that the integral of dt is just t, right? Because that's how integration works from the bounds from 0 to t. And now on this right-hand side, we need to recognize, well, the integral of 1 over x minus a dx, where a is a constant, is equal to ln, well, x minus a, right, plus c because it's indefinite, but you get the point, right? Even on your equation sheet, you can see that if it's 1 over x minus a or x plus a, right, it'll be ln x minus or plus a, depending on if there's a minus or plus here. So I'll just do that same thing over here with that rule. And this integral will turn into ln q minus q infinity from 0 to q of t. 0 to q of t. And now these are both of the sides of the differential equation. And now we have basically, I guess you could say we got through the solving part. Now we're just going to simplify, right? So this left-hand side will get 1 over tau. It will turn into, not get, t minus 0, right? And t minus 0 is just t because the right-hand side will be 0. And this turns into negative t over tau, right? See, that negative is there. I told you it would show up again, right? This term, I've referenced it before. And for our right-hand side, we'll have ln, what was it? Q of t minus q infinity minus ln 0 minus q infinity, right? And notice I'm only plugging in q of t and 0 for this variable because although q infinity is a q, right, it's not a variable that I'm integrating with respect to or subbing in with respect to. It's a constant, right? We said that earlier. And now I'm going to use my rule of logs on this right-hand side to combine these two natural logs into one log. And that rule of logs, I'm going to write in a different color, is ln a minus ln b is equal to ln a divided by b, right? And applying that to this right-hand side, we can combine these two logs to get ln q of t minus q infinity divided by negative q infinity, right? Because that 0 makes it so that this log is as if we just took out that 0, right? It's the same log. Oop. And now that's our right-hand side, and we'll set that equal to our left-hand side, negative t over tau, right? And now I'll continue this derivation, and I'm going to think, well, I want to isolate q of t because the entire problem that we were trying to solve was to derive charge as a function of time. And now I see it in this equation and I can just algebraically solve for it. So now how am I going to isolate q of t? Well, I see this log that's encapsulating it right now, this natural log. So I'm going to get rid of it by raising both sides to e, right? That's how you would, that's a rule, right? The rule actually I should specify is that e to the ln2 is equal to 2, right? So then e to the ln of this entire thing is going to be equal to that entire thing that's on the inside, this inner term, q of t minus q infinity divided by negative q infinity. And knowing that, right, I can just say that this e to the negative t over tau is equal to q of t minus q infinity divided by negative q infinity. And now in order to isolate, I'm going to multiply both sides by negative q infinity. And I'm going to get negative q infinity times e to the negative t over tau is equal to q, right, because these cancel, q of t minus q infinity. And now, in order to isolate, I'll just add q infinity to both sides. And I will get that q infinity minus q infinity times e to the negative t over tau, t over tau, is equal to q of t, right? And just to rewrite, because this bothers me a little bit, we'll factor out that q infinity, right? Because factoring out, we would get 1 minus e to the negative t over tau. Just to make this a little bit more nicer, a little bit cleaner for our final answer, we'll get that q of t is equal to q infinity times parentheses 1 minus e to the negative t over tau, close parentheses, right? And this negative is the one I was talking about earlier. You'll see something that always looks like this form whenever you're working with something with circuits as a function of time, right? The one, I can say that won't always be there, but you'll always have, for AP Physics C, a negative t over tau, something that looks like, and this has to have a negative, because otherwise it wouldn't describe the behavior of the circuit correctly. That's why I multiplied -1 to the differential in the first place, right, before solving this equation, in order to get this negative t over tau, right? But now, if you recall correctly, we'll go back up here, I left this other differential without multiplying -1 here. I did not solve that one. But I'm going to do that right now. So if you would like to stop watching the video here, it's really your choice. This is where method 1 ends and method 2 begins. Okay, so now I'm going to do method 2. You'll notice I replaced the left-hand side with method 1. So method 2, I'm going to bring this side down, right, just to rewrite it so we can bring it nice smack dab in the middle so I won't have to be working up against the edges of my screen. And I'm going to again separate my variables, matching this q with this dq and dt with, in this instance, constants, right? Because there's no t variable. But if there was, I could just integrate it the same way. I would just separate the variables the same way. But I'm going to do that, right? Sorry, spaced out. I'm going to multiply 1 over tau times dt to both sides. This is a nicer tau. And doing that will cancel my tau here, cancel dt here, and I'll get dt over tau times q infinity minus q is equal to dq. And now I'm going to separate fully by dividing by q infinity minus q, q infinity minus q. And I'll get that dt, 1 over tau times dt is equal to 1 over q infinity minus q, and dq, right? So now I have this expression. And last time when I had this, there was a negative on this side, and this expression was kind of flipped, right? It was a positive q minus that, right? But that's when I multiplied the negative. So in this instance, I'm not going to do that, but rather I'm just going to integrate right away. This is method 2. And if you recall, our limits were 0 to t from 0 to q, right? q of t. So integrating the left-hand side, we'll take out our constants and we'll get the integral from 0 to t dt. And the right-hand side I'll leave alone because I want to just simplify the left-hand side for now. 1 over q infinity minus q dq. And this left-hand side integral will turn into 1 over tau, t from the limits of 0 to t, right? Because that's how integral calculus works. But this right-hand side integral is a little bit different, right? What you need to take into account is that the integral of a function 1 over ax, right, plus b dx, that integral will evaluate to 1 over a ln ax plus b, right? Plus c, of course. So this is a rule of calculus, and the way this rule is derived is through u substitution. Now, I won't go through the u substitution today because all you need to do for this class is memorize this rule, right? And then another small little note. If this is ax minus b, well, then what the integral evaluates to will be 1 over a ln ax minus b. Really, it doesn't matter if it's plus or minus. You'll just change the answer accordingly, right? So now applying that to this integral, I'll rewrite the right-hand side so it's just a little bit easier to apply this rule. I will write 1 over negative q plus q infinity dq. And now you'll see that I'm integrating with respect to dq, right? Like here, I was integrating with respect to dx, right? Or integrating with respect to x, not dx, and integrating with respect to q, not dq, right? You'll notice that the coefficient, right, the coefficient a is -1. So this right integral, this right-hand side, will be 1 over -1 ln, right, negative q plus q infinity from the limits of integration from 0 to q of t, right? Simple enough. That's where this rule in pink came in. And I'll leave that there if you'd like to see it. But now I'm going to move on to the left-hand side. So actually applying the fundamental theorem of calculus, this left-hand side will become t minus 0. And like earlier, like you might have seen, the t minus 0 will just be t over tau because that 0 doesn't contribute anything. It really doesn't matter. You can just take it out. We can move on to this left-hand side, and we'll leave that -1 out and simplify, right? So the inside will be ln, and we'll sub in, right, negative q of t plus q infinity, and write fundamental theorem of calculus, ln q infinity. Or, well, I should write it for you guys. ln 0 plus q, I will move this, plus q infinity. Kind of tiny, but hopefully you can see. And now I have this big -1 that I could apply, right? And I could change this, but I know from the last solution that I need -1 to be with my t over tau, right? So I'll just multiply -1. I'll just multiply -1 to both sides, right? And now this is something that's really important for teachers to teach, right? It's really imperative that you understand that you need to have a negative times your t over tau. Otherwise, you'll finish your entire derivation and then you'll be like, wait, why is my answer wrong? You'll be like, why is it e to the t over tau? Why not negative? It'll be incorrect, right? Sorry, it won't be incorrect. It'll be harder to simplify, and that's really not what we want. So it's imperative that you multiply this negative t over tau. So we're going to have negative t over tau, and that -1 will cancel over here. And this will become ln negative q of t plus q infinity. And then that rule of logs, I'll apply that here, divided by q infinity, right? Because ln a minus ln b is equal to ln a divided by b. That's what I just did here to get to here. And now, in order to cancel that ln, I'll raise both sides to e, like I did earlier, and I'll get e to the negative t over tau is equal to negative q of t plus q infinity divided by q infinity, correct? And now I'll multiply q infinity to begin to isolate q of t. And if you see where this is going, you'll notice that, wow, they are the exact same answer, right? These q infinities will cancel. I get negative q of t plus q infinity. And now I'll add q of t to both sides in order to make it positive and not negative, right? Because I don't want negative q of t. No, I want q of t. The charge is a function of time. I don't want any multiplier by it. And then on that right-hand side, we have q infinity left. And now I can subtract q infinity times e to the negative t over tau to both sides to get q of t by itself. And you'll see that q of t is equal to q infinity minus q infinity e to the negative t over tau. And then if we factor, we get q infinity 1 minus e to the negative t over tau. And that's it. That's pretty, that's the pretty much the final derived equation, and it is the same as the one we did with method 1. The only difference between these two methods is one, I incorporated my -1 earlier. The other one, I did not, and I just separated my variables like regular. But at the end of the day, whenever you're doing these circuit derivations, whether it's RC or LR, you are going to need e to the -t over tau. So ensure that before you solve for whatever it may be, q of t, v of t, um, whatever of t, ensure that you have -t over tau as a term. Ensure that, you must ensure that. It has to be there before you raise e to anything, right? Like I did here. This negative has to be there before you do the step. That is imperative. I cannot stress that enough. Um, but hopefully this video helped you guys, and hopefully you understood some more from this, and I'm very glad to be making this video. And I'm also very glad to be showing you guys physics as always. I appreciate all of you for watching my videos, and I hope you guys have a blessed day. I'll see y'all.